Now, just a few of us hate fractions, so maybe our mental math would have just like shut down on us and been like, it doesn't work nicely. But how did you get to 11/5? And then my question is why or how was it legal? But first, how did you get there? 5x plus 1 had to equal? Look at us, on topic, talking, so proud of you. So, 5x plus 1 equals 12. Simple algebra says subtract and divide, even if you don't like it. That's true, right? But that wasn't my only question that I wanted groups talking about. Do you remember what else I asked you to talk about?
Why is it equal?
Why can we go from here to here?
1-to-1
I heard multiple things. I heard Nathan saying 1-to-1 property. Maybe there's something in our book we didn't talk about yesterday that makes all of this legal. But then Nathaniel, I think yours is more a common sense one. What do you think? Yeah. The logs are the exact same type. So if the logs are the exact same type, and now here's something that our brains probably wouldn't really understand, but it's really important as far as more complicated functions. If the logs are the same and, okay, if the logs are the same, aka with the same basis, and logarithms are 1-to-1, then we can say the following. Now, some of you are like, no, it doesn't matter. Like, whatever's there has to be there, so whatever's inside has to be the same. Here's a quick tip for you. In harder functions, if the function was not 1-to-1, we wouldn't be allowed to make this jump, even though the logs are the same. Which is really weird and kind of mind-boggling. Wait, there's another way this could be true, even if the logs are the same. Now, no, don't worry. Logarithms are 1-to-1. Which means each input has one output, each output has only one input, so we're okay. But there are functions out there that are not 1-to-1, and this whole logical jump would be illegal. So careful, but in logarithms, we're fine. We can make that logical jump. So therefore, that's true. X is equal to 11/5. The logs have the exact same base. Good, Nathaniel. All logarithms are 1-to-1. Good, Nathan. But we didn't actually write that in our notes yesterday, did we? Notes open. We did not write about, now we did with exponential functions. We said exponential functions are 1-to-1. And so some of you just used the exact same idea with logarithms, and you ended up being totally fine because logarithms are 1-to-1 also. So it didn't really mess you up. But there were some properties that are kind of important that we didn't write down. And I think a lot of them were logical. That's why I still had homework due today as far as you guys attempting. Sorry, I think there was one graph on last night's homework, wasn't there? Yeah. I said no graph, there was one. You were allowed to put in your calculator and just see that they flipped across the y equals x line. That's all that was supposed to be for. It wasn't meant to be a tricky one. More graphs are coming tonight. Well, let's get this into our notes, and then we'll talk about homework and how it went. Nathan, go ahead. Properties of logarithms. If you guys remember, I said this chapter was like the puzzle chapter. But we won't be able to play. And to be specific, the playing section is section 3.4. We won't be able to play, or at least be able to play well, or in a way that we can actually win in section 3.4 if we don't get the fundamentals down. Even if you have somewhat of a weird, ambiguous, vague idea of what a logarithm is, you're not going to rock that section of puzzles, section 3.4, unless you have the fundamentals down. And this table is super important to that end. Now, this table's kind of small. It's kind of zoomed out. It's going to be awkward in that it's going to be like off the page, but let me make it a little bit bigger. Some of you are trying to see and straining your eyes. Hold on. There you go. That might help just a little bit. Whenever you see a log base A, what are they saying? Are they saying the base will matter or the base doesn't really matter at all? keeping it general. This isn't a log base 2, it's not an ln, it's not a common log, it's any log. Any log of 1, always 0. Because regardless of what the base is, any base to the 0 power is 1. Except for 0. A can't be 0. 0 to the 0 is actually undefined. But any non-zero number raised to the 0 power is 1. Log base, I don't care anything of that same anything, always 1. Because if the log is a power, any base to the 1 will be itself. Cool. Log of any base a of a to the x will always be x, and a to the log base a of x is always x. I'm freezing the screen so you guys can finish writing it, but I'm pulling back up my graphing calculator because that number 3 and that number 4, all of them are super important, but those are the ones that we're going to use the most. The inverse property and the one-to-one property. And to be honest, the inverse property is the most important because it allows me to undo an exponential, or it allows me to undo a logarithm. So what if? We'll pause here. Most of you didn't skip a line, right, underneath the table? Okay, that's okay. Just pay attention. I can write it here. What if I was to give you, let's get back to the home screen and let me unfreeze the projector and lose my batteries in the process. What if? Let's get rid of all this stuff from yesterday. What if I was to show you the equation? Here we go. Log base 2 of, I was using log base 2 yesterday also, huh? Okay. You don't like that? Sorry, I'm really trying to break the habit. Log base 2 of x plus 1 equals 3. You have nervous tics too? It's not really nervous, it's just like if you're bored. Some of you click your pen, some of you play with games. Coming back. Log base 2 of x plus 1 equals 3. We talked yesterday that even an algebra 1 kid would know the final purpose or the final goal, right? What's the final goal? Find x by itself. Yeah? Okay, that's easy. But what did we talk about yesterday is harder in algebra 2 and Precalc? What's been put into an equation that makes it too complicated for an algebra 1 kid? The log. Algebra 1 kids know how to subtract the 1, hopefully. Know how to divide if there's multiplication. Maybe know how to square if there's a square root, probably not. But you guys, don't we need an inverse operation of a logarithm to get rid of it to get to the x, right? So, according to our notes, what you guys just wrote down, hold on, we'll get back to it. The inverse property, number 3, put a huge old star by it if you have a highlighter. This is the most useful one as far as solving our puzzles in section 3.4. And we have easier ones along the way, but that's the section where we really get to have fun. What does this property tell me I could use to get rid of the log? Which one? The first one or the second one tells me how to keep going in the equation that we're kind of working on over here. The first or the second? The first says if I can put an exponential inside a log, the log could go away. Guys, algebraically, is it legal for me to put something inside? Can I put a 2 to the power of inside the log base 2 to make the log go away? That doesn't make sense. What do we always do when we're solving? Don't we do it to the outside of the equation? Subtract 1 from the whole thing. Divide the whole thing by. Multiply the whole thing by. Square the whole thing. We have to do it to the whole thing. So even though there is a property that sometimes is useful that says, hey, log of an exponential, they all cancel out except 4. That's not helpful in this one. The one that's helpful is the second one, because check it. If I have a log already, what can be done on the outside that makes it go away? What can be done on the outside that makes it go away? 2 to the power of. Is that legal? Well, not yet, because algebra tells me what I do to one side, I must do to the other. But how do you undo a log? According to the inverse property, I can undo a logarithm by making it the exponent of its base. 2 to the power of log base 2. Guess what's going to happen? X plus 1. They, in a sense, undo each other. In a sense, they cancel each other. So 2 to the power of log base 2. How do I get rid of a log? Oh, just base to the power of. But what you do to one side, you have to do to the other. So what's on the other side? 2 cubed, which is 8. So therefore, my final answer is going to be 7. Now, why am I over here on the screen? Why am I under calculator? Do you remember what I showed you yesterday with the squared and the square root, the log and the 10 to the power of, the ln and the e to the power of? What's the relationships of each of these? It's inverses. So how do I undo a squared? A square root. How do I undo a common log? 10 to the power of. How do I undo a natural log? E to the power of. How do I undo any log of any base? Base to the power of. Now, some of you are like, there was an easier way to do that. Okay, there was another way to do that. What's the other way to solve this equation without thinking of inverse properties? What did we learn yesterday? We can do with logarithms. Does anybody know the snail? Joe Tan just showed me yesterday. He said Victor knows it too. No? No snails? Not for logarithms? This is called logarithmic form. Why? Duh. What is there? A log. Mr. Chase should have told you about exponential form and how there are ways to go back and forth from one to the other, from logarithmic to exponential, exponential to logarithmic. Why am I talking about a snail then? Because it works with base to power equals. I don't know. Kids learned it in their Algebra 2 class and they like it and they still use it in Calculus BC. Why not? The snail says to go from logarithmic to exponential form. What math did you do? I didn't really. I just changed the form. Over here I did math. Over here I undid the log. The way that we like to undo things in equations to get x alone. Over here I was like, there's this relationship thing about how to rewrite one of those. Do they both work? Yeah. Does it matter which one you use? Kind of no. Kind of no. But can I show you just a peek at it? Can I go to section 3.4 and show you just an example of one of those crazy equations we're going to see soon when we build up to being able to see it? I'm showing you a peek now. Okay. In section 3.4, if you only know the snail, from now on, when I say the snail, what am I talking about? Changing from logarithmic to exponential, because if you get rid of the log, nice things happen. X is 7. But what if I was to show you this example? Let me see if I can find it. There's section 3.2b, there's section 3.3, there's section 3.4. Hold on. This one. Snail. Why not? Do I have just one logarithm that I can get rid of? No. Are there other ones? Other ones? Other ones? Okay. Oh, that's one-to-one property. We could do that one without a snail. Anyway, there are harder ones coming. I'll come back to the one that I was looking at a second ago. I think we need more skills, more tools, more tricks to get x alone. Because right now, x is in 2 different spots. There are 2 different logarithms. I can't just do a snail to make it all better. But wait. We're not there yet. Could you have just changed the form to make it better here? Yes. But is it important to know the inverse property? Is how you undo a log? Yes. So in your notes, what were you just taking? I need to get back to section 3.2. I need to get back to where we are not looking at where we're going, even though it's important in life to keep an eye on both along the way. Life lesson. 4, this page. The inverse property shows us how to undo an exponential with a log or how to undo a log with an exponential. The key is how do you undo, and it's all right here. And then the one-to-one property, you guys already figured out. You showed me at the beginning of class. It just comes naturally to you, which is perfect. Some of you might have gotten confused. I think this was an actual homework, or at least it was super similar. What do we do if we have log base 11 of 11 to the power of? If logs and exponentials undo each other, what's that final answer going to be without a calculator? 7. It's as easy as that. That's what this inverse relationship between log bases and exponential with the same base does. How about log base pi of pi? Because it's pi to the what power? 1. Oh, and there's also the log base a of a is 1. And then how about log base 3.2 of 1? Yeah, because, check it. Think of your snail, worst comes to worst, right? Oh, that's a bad snail. I don't know what's going on there. Remember, you're trying to answer with whatever power of 3.2 would give us 1. Well, guys, what power of 3.2 would, well, what always gives us 1? 0. Okay, I just want to make sure that we have these properties down in our notes. We didn't get them down yesterday. Some of them are so basic that I think you guys would have been fine without them, but just a couple might have confused you. We're not going to grade all of our homework right now because technically, remember, you're still doing homework 20 tonight, which is still in section 3.2. But are there any places you guys got stuck that you want to discuss really quickly? It's not so much about whether or not you got the right answer, whether or not you did it perfectly, but you were just like, I'm confused. Anything we didn't cover yet? Yeah. Oh, what number was that?
There's that was from like 3.2b. The graph one.
Just give me a number. What number was the last one on the homework 19? 33. Yeah. So I was just kind of getting you into the graphs without totally getting you there. Don't worry, we're doing graphs today. Oh, does it not ask you to do anything else besides just sketch? Sweet. Nice, Emma, thank you. It's an intro to today's notes. Ready? Boop! How do we sketch stuff if we don't know it off the top of our heads? Wait, to say a calculator, but I mean like actually sketching. Make a... Yeah, like plot points. Make a table. So couldn't I for F... What's the easiest power that we all know? 0. So can't we plug in 0 and say, oh, anything to the 0 power is... Okay, that's not bad. Isn't 1 going to be pretty easy too? And 2, sure, why not? Hey, what would negative 1 be? 1 over 7. Man, it's going to get really tiny that way and really big that way. Isn't that what exponential functions look like? At 0, we have the intercept of, this was reviewed from section 3.1. At 0, we have 1. At 1, we have whatever base it is, which I'll go ahead and just put 7 up here randomly. Should be a lot higher. And then 2 is going to be, oh dang, super high, right? But 1, 7, well, he's just super low. So there he is. Now, could you have made a table for log? Technically. Literally, yes. You could have made a table, right? But what do you know about exponentials and logs just from? And what do we know about inverses? Chapter 1. What do we know about inverses? Graphically. They just flip. Like how? Diagonally across the y-axis. So couldn't we technically have said, hey, if he has 0, 1, he must have 1, 0? Hey, if he has 1, 7, then he must have 1, 2, 3, 4, 5, 7 1? If he has negative 1, 1, 7, he must have 1, 7. So let's see, negative 1. Took me a second, sorry. So technically, you could have just graphed the inverse and not even had to worry about the logarithms, or you could have actually practiced what you know about logarithms, like if you tried to plug in 0, it's going to be DNE because every log, wait a minute. Huh. Exponential functions have what kind of asymptote, guys? horizontal. What is that going to mean about the inverse? Vertical. So without us even talking about graphs yet, we could say right now that a logarithm at 0 is always going to not exist, because it's going to have a vertical asymptote there. I think that's important for today. But we already knew that any log of 1 is 0, so we could have kind of plotted that point pretty quickly. And then maybe you knew log base 7 of 7 is 1. You could have gotten a few points. But yeah, and then those are just a couple ideas of how you could have done it without us going over the notes that we're about to go over now. Notes! Here we go. It's time for graphs. And that was a perfect lead-in. Because every logarithmic graph could have been gotten by its exponential inverse counterpart. So I'm going to write a to the x just as a point of reference. Because let's be honest, which one are we more familiar with, logs or exponentials? Yeah, totally exponentials. I would much rather see an exponential, I think, if I was at your level, than a log. And at my level, if I see a log, I really hope it's an ln. That might not make sense to you guys because you don't know calculus yet, but if I see a log, I would much rather be an ln. Okay, so the next thing is, if we have an a to the x, whoop, there he is, and we can even put his important points like 0, 1, and like, I don't know, 1, whoever he is, 1a. We could be really snazzy and have 3 points and do -1, 1 over a. Those are like our 3, what do we call them, representative points? The 3 main points of our parent function for a to the x. Logarithms just flip it. Which means I have the point 1, 0. I have the point whoever a is, 1. Log base a of a is 1. And then I can also have log base a of 1 over a is -1. I think those are kind of the 3 points I just did. Cool thing about inverse relationships, the x's and y's of the one that we're more familiar with can lead us to the x's and y's of the one that we're not so familiar with. Okay, so let's fill in what we know. Domain, x's, right? How left, how right? How left does this guy go? He does go to -infinity, but not his x's. Those are his y's, right? The y's go forever low and forever high, not very quickly, but it is headed up. But what about the x's? How left? But it can't hit 0. So, check it. I told you at the beginning of the year that logarithms have a restricted domain. We had domain problems. Denominators. Square roots. Is that it? I think I wrote logs, but I put it in parentheses because we weren't there yet. Guess where we are? There. So, if you have a log, any log, of any base, of any argument, whenever I'm trying to say it doesn't have to be an x, it could be an x plus 1, it could be an x squared, it could be something else, I put a u. It's a calculus thing, just work with me. You saw me do it earlier this year with square roots and denominators. Domains for logarithms say u have to be greater than 0, and there's always a vertical asymptote at 0. Now, if it's just x, no big deal. X equals 0 is the vertical asymptote. I don't know how I was saying that. There it is. But as soon as it's something other than just x, no big deal. Plug them in, solve. Plug them in, solve. You can find your vertical asymptote by finding the 0 of the argument, and you can find the domain by making the argument greater than 0. So we can put that right here, right? X equals 0 is the vertical asymptote, and if there's something other than x, whatever, find the 0. Do you remember what strictly monotonic means? No. Only behaving one way, which is increasing. Unlike parabolas, is it going to show up or is it going to disappear? unlike parabolas that decrease and increase or increase and decrease and change behavior, logarithms are like exponentials. They go faster or slower, but they're always going up. And then the x-intercept we already wrote was 1, 0. There you go. If you remember section 3.1, we did this for exponential functions too. Super similar. Talked about his characteristics. He just had an HA instead. His range was the domain, and his domain was the range, because inverse functions, they flip. But after we talked about the parent function, where did we go next? Do you remember? We talked about the parent, we talked about the basic, and then we transform. Same thing. So B, what is he? Shift, dilation, reflection?
B is shift up or down.
Oh, no.
It's a shift vertically.
It's a shift vertically. Why? Because it's
On the outside.
adding on the outside. Or it could be subtracting on the outside. B can be a negative, B can be a positive, so I have a shift up or down, right? So who's going to be my horizontal shift? C. Some of you guys, I moved you back and now you're not talking anymore. Ethan and Dylan doing a great job. This one's sleeping. I'm hoping it's because we're tuned in. Just because I move you far away doesn't mean I want you to stop talking. Usually it's because I want the whole class to hear the things that you're saying. Who's A? Is the base, right? The base ends up kind of stretching and compressing. Now, I didn't show dilations because the base isn't a dilation. It's just log base 2 is going to look a little bit less steep than log base 7 or log base 10 or log base 11. The bigger the base, the faster the exponential goes, which actually means the more flat the logarithmic one goes. I didn't put dilations because if I did, this would start to get real nasty real fast. So I just showed you the basic ones. There can still be dilations. I just didn't put them. But the other main important thing that you're going to see.
Dilations would still go in front of the log?
Yeah, you would have like a, let's see, I guess we could do D. You could do a D times the logarithm.
Okay.
And that could stretch it or compress it vertically. And then you could throw like an EF something or other right in there. But see too many letters. But you could have reflections. And so reflections across the x-axis. Hold on, let's think about it. A logarithm goes like this. So across the x would go like this, right? Which would be kind of weird. But the vertical asymptote wouldn't shift. He would still be at 0. That would need a vertical reflection, which means a negative on the outside. So you could have like a negative log base. And then if I wanted to go the other direction, I would need a horizontal, which would throw it on the inside, which is weird because you're like, logs can't be negatives. Well, but negatives of negatives are legal. So that actually flips him this direction. And once again, vertical asymptote doesn't change. So let me do a quick reminder over here. The vertical asymptote, just like the horizontal asymptote was helpful with exponentials, the vertical asymptote can be helpful with logarithms, but we can always find it by setting whatever the argument is the VA is always going to be at u equals 0. And technically, you could say u not equal to 0 because the vertical asymptote is where the function can't exist. But we can always find the vertical asymptote by finding the 0 of the argument. I don't know. If you do the shifting, you should kind of bring the vertical asymptote along with it, but that's a quick little trick. So, let's get us a transformed one, huh? Sorry, a couple people still writing. Let's get us a transformed one to play with. So what if I was to give you a log base 2? I don't know know why I'm liking log base 2 so much. Probably because it's one of the smallest bases that we can do. Log base 1 is boring because 1 to any power is still 1. He doesn't do much exciting stuff. But you guys, tell me an important point on log base 2 of x. What's a point I can put right now? Negative 1, 1/2. That's the first one I heard. And I almost like it. The problem is I can't put a negative into a logarithm. So what's the right point? That's an exponential point. The logarithmic point would be, okay, so I can do 1/2 negative 1. Because log base 2 of 1/2, 2 to what power is 1/2? Negative 1. That's 1. What else? 4, 2. Log base 2 of 4, 2 to what power is 4? 2. You're right. 4, 2. But the easier one probably would have been 2, 1, right? Because log base 2 of 2. But what's the one that everybody missed that's the same for any log? Okay. Try to be all snazzy. Where's the vertical asymptote? At the 0 of the, x is 0. Okay, there you go. At the 0 of x. Got it. So what happens when we go to graph G? We'll talk about transformations, but where's the vertical asymptote? Not negative 1. It's the 0, and the 0 is 1. So right away, we know the vertical asymptote for him is going to be right there. But that's okay. Let's talk about the shifting. How does this guy shift? 2 up and 1 to the right. So can't I take each of these and say, okay, I'm going to go ahead and shift. Sure, why not? 2 up and 1 to the right. Wait a minute, that doesn't make sense. Oh, because it was 1/2. 2 up and 1 to the right. Got it. 2 up and 1 to the right. Got it. 2 up and 1 to the right. And then 2 up and 1 to the right. Something like that. And if you shift your vertical asymptote also, it's not going to be that bad. Because the vertical asymptote 2 up made absolutely no difference, but 1 to the right, haha, there he is. And now I know what to skim. See it? Where's the vertical asymptote for this guy? The 0 of x is 0. So actually, he doesn't shift horizontally at all, but you can see that x minus 0, there's no shifting left or right. Oh dear, but what happens?
X-axis reflection and vertical shift up 1.
Which one happens first? Do you flip and then shift, or do you shift and then flip? Does it make a difference? Because if I go up 1 and then flip it, or if I flip it and go up 1, does it change? What if they're different? My brain's not seeing it. Is anybody's brain seeing it? You go up 1,
You go up 1 and then
flip,
flips down to the new.
right?
Yeah.
But if you flip and go up,
It's different.
flip 1's lower. That's okay though. Let's get the right one, then we won't have to worry about it.
Do the up 1 first, then it's different.
Yeah, I think it's a little different. Like 1's lower. You can graph both of them and see. Huh. Long story short, you're going to need to flip and then go up 1. There is a method to the madness in order to the transformation. Kind of like PEMDAS, we think of multiplication and then addition, if that helps. So if we reflect and then go up 1, this one's nice because he's not going to reflect, so he's just going to stay. He still has to go up 1, so it's like, well, okay, there it is. This one, if I'm going to reflect, he's down at negative 1, but then up 1, got him. That one, he's going to reflect, which will be at positive 1, and then up 1, he's going to be up about there. And once you have a few points, you should be good. But if worse comes to worse, hit it. And if you get to one of these where you're like, wait, they're going to be different, can't you always, always, always go back to a table? We know that any log of 1 is always 0. We know that log of 2, that's where I would go next. Log base 2 of 2 is 1, and 1 minus 1 is 0. So we could double check that we've gotten him. I have the 0.20, got him. And then what's another one that I know? I know log of 1 is 0, log of 2 is 1, log of 1 half, right? Log of 1 half is negative 1. 1 minus negative 1 is 2. There you go. I have 3 points. So I have 1 half 2. Got him. I have 1, 0. Nope. Did nobody catch my math mistake? What's this supposed to be? If I plug in a 1, what's log? Any log of 1? What's 1 minus 0? 1, 1. Got him. And then 2, 0. Got him. Proper order, reflect, and then shift. They're super similar. But one of them is going to be lower and one of them is going to be a little bit higher as far as those of you guys trying to figure out the order. So, nice thing is, I've already told you guys this page, you might need to write it, you might not need to write it, because some of it's just review. What happens to inverses graphically all the time? They always reflect across what line again? Y equals x. All of our x's and y's switch, and so depending on which one you like better, and you guys can't see it, I just have that log base 2 basic graph of an exponential and a log that aren't transformed. If your brain works better with exponential, graph his points and then flip them all. And if your brain works better in logs, which is basically no one, I guess you could graph him first and then flip. But the same thing happens to domains and ranges, right? If all the x's and y's switch, the domains and ranges switch too. Okay. Graphs. We talked about the asymptotes. They're vertical this time for logs. We've talked about domain with vertical asymptotes. We got to be careful. We've talked about intercepts, and we've talked about if you're like, I don't know what to do with the log, do the exponential, and then change it to logarithmic form. The struggle is if you have transformed functions. I wouldn't do that with transformed ones. I would go back to the parent function. I would get the basic logarithmic graph, maybe using the exponential to get him, but then start shifting those important points. And life gets a lot better. Remember, we did mark those important points in our basic graph, right? We're taking log of a 1 over base, or log of a 1, or log of a base. They're really easy to plug in, and that's exactly what I used in this table for this green one, where we were a little confused as to what order to go. I don't remember why exactly I had this example. I think it just shows up at the end of homework, and so when I was trying to split the homeworks up, it shows up in this homework instead of the last homework. But guys, this is just a plug and chug. What would my final answer be? Next homework will mostly be graphs, but you might have a couple of these from the end. -4, why?
Because ln is the inverse of b.
The relationship of ln of b is an inverse one. So therefore, they I don't mind you guys saying canceling. Technically, they undo each other. They kind of reduce away, but that's okay. And we end up with the power of -4. Section 3.2b, I believe that is the end. Let me make sure there are no other hidden homework helps after the fact. I don't think so. Anybody who's in 3.2b, I know there are some of you out there. Are there any places you've gotten stuck in the homework that some kids haven't even seen yet? Anything you want us to talk about? Any tricky ones? No one stuck yet? Sweet. Here we go. Section 3.3. I think we might just stop here. 3.3. First page.
Oh yeah.
There's a problem. One of us hasn't taken it yet. So I'd love to give you your test. They are on MedWeb. I believe I have updated it. But the person who hasn't taken it yet, you need to come find me and we need to take it. If you don't come find me today, it'll be in class tomorrow that you need to take your test. But if you want to see your test, you can pop by at any point today. The grades are on MedWeb though. Alright, that's one page and then we're done. Just one page, then we're done. Nice thing is, those of you guys working on 3.2b, how hard is it? Okay. So it wasn't like spectacularly easy. That was more like 3.1, right?
Okay.
But you didn't hear them necessarily totally stressing out, so shouldn't be too bad. P.S. kiddos, your Red Lab grade says they're up to date. Please, if you have any missing work, I love accepting it for partial credit. I mean, I'd rather it be full credit, but I'd much rather put in points than have your grade have zeros. But just a warning, there is an end of a grading period deadline coming next Friday. Any missing work that has not been turned in from the entire year up until that point. Next Friday is the expiration date for you guys getting partial credit, okay? So if you didn't turn in notes one time, or if you have a missing homework spiral, or if you have some Google Classroom stuff, remember if you submit it late, just throw a comment on there. Or if you were absent for, I think we got all the kiddos absent for quizzes caught up. Still have one test. Just check out Brenda, let me know if anything looks funny. Yeah. Is it missing? Yeah, there you go. And then the grade sheet changed a little bit too because of the updated textbook. What's the change of base formula, guys?
Oh, the log A.
How does it go?
Log B.
Of
A.
X. There you go. The X goes on top, the A goes on bottom. What does that mean when we get down to this? Can I cancel them? No. Good to hear. But what can I do? The addition of exponents, you guys remember how I opened the exponent rulebook underneath the webcam a couple days ago? Where does addition in the exponent come from? Multiplication of like bases. So why would I write it this way? Now I can simplify because I have an a to 1 log a, an a to 1 log a. If I have a plus or minus, I can't just distribute raising powers. But I can legally split up the powers. And what does this actually end up becoming? Not u plus v, but u times. But what on earth does that mean? If I throw a log base a on both of them, doesn't log base a of a cancel out? This is why when you add two individual logs, you can end up combining separate logs into a single with multiplication. You guys remember the product and power and quotient properties from last year? This is basically all we need to figure out and to master in order to be able to make it through tricky ones in 3.4. We're doing a good job, guys. Finish up 3.2 tonight. Bring A and B. Great. The puzzles are coming. Will you be ready?
Oh crap. Sorry. I just my phone fell off.
It's gonna struggle. Your hydro, your phone.